today's webinar, Integrated Approach to Motor and Lead Screw Technology. Now I'd like to introduce our presenters. Jamie Stockton is Global Product Manager for PVC Linear. He has been in the industrial automation market for a decade, offering engineering support for both mechanical and electrical solutions. He has deep background in diverse applications, including packaging, medical, aerospace, defense, and various food-grade situations and applications. Andy Sklorenko is the Sales Director for Moons Industries of America, Inc. Andy has worked in the industrial automation market for more than 14 years, focusing on electromechanical products and working with customers on applications across many industries. His goal is to bring value to his customers through his engineering and customer service background. And finally, Mike Maroney is the Application Engineering Manager at Applied Motion Products. Previously, he worked as a design engineer at AMP, where he contributed to the design of several motor drives and played a central role in the development of CAN-open compatible drives and integrated motors. More recently, he has worked in the medical and industrial device market. And now I'm going to turn the presentation over to the speakers.
All right, thank you very much. Hi, this is Jamie Stockton. Thanks for joining us today. What we're going to do is go over PVC's integrated approach to motor and lead screw technology. First of all, on the agenda, we're going to go over the foundational elements of a lead screw motor, including the control, motor, screw, and the nut. And then we're going to go through some of the applications that are typically seen for this type of product and kind of explain how using the PVC solution is going to help optimize and make those solutions as good as possible. First up, let's go over what a traditional mechatronics-based solution looks like. You're going to have the screw and nut. Of course, there's two different types of screws involved. You've got a lead screw, which is going to be typically a metal or plastic on the metal screw, or you may have a ball screw, which is essentially rolling element balls traveling on the screw. Typically, those are going to be the two types of screws that you're going to see. You're going to have interface hardware. The screw must connect to the motor. In a traditional system, you'll have a coupling. And if you have the motor to the system, you're going to need some type of motor adapter, say like a NEMA 17 or NEMA 23 adapter. I'll let Andy talk about the different types of motors that you might see.
There's many types of motors, obviously, that Moons manufactures, and with an integrated product, we could look at a traditional stepper, NEMA 17, 23, or any variety of those depending on your loads and torque requirements, as well as a step servo product, which Mike, I'm sure, will highlight from AMP, which brings the technology closer to a servo-type performance with a stepper-type commercial side.
Applied Motion Products part of this picture is that we make motor drivers and integrated step motors using the Moons step motors. We have both open and closed loop drivers, including the step servo technology that's shown there, and that effectively puts a closed loop motion controller on the back of the stepper motor, which enables, like Andy was saying, the servo style performance in this cost-effective integrated package, and we'll talk about that a little bit later. Moving on to the controller side of things, in the traditional arrangement here, the motor drive physically sits between the controller and the motor screw combination. On the bottom there, we have a standard motor drive. AMP drives all have built-in I/O and come in a wide variety of control options, from step and direction, locally stored programs, to a full range of field bus control options. This motor drive on the bottom is effectively identical to the one on the back of the step servo smart motor next to it, meaning you have a choice of where you want to put the drive electronics, either directly on the line attached to the motor or back in your control panel where you cable out to your motor. And then on the top there, we see a PLC. For many traditional applications, a full-time controller like that PLC is in the mix, either to coordinate motion across multiple axes or even just to monitor the status in a little more detail than using the drive's digital outputs. As I mentioned before, our drives support a wide variety of these PLC control options, from step and direction to various field buses. Really, the drives can interact with pretty much any PLC you throw at it to enable control of this traditional motor lead screw system.
All right, that was what a traditional setup would look like. And now this picture will kind of go over what the optimized PVC offering is going to entail. We've got the lead screw and the lead screw nut. As you can see, and we'll talk about a little bit more later, the coupling and motor mount adapter are not present. as we've directly coupled the screw to the motor. We've got the Moons stepper motor, which is a hollow shaft, as you can see from the picture below. Andy, maybe you could talk about that picture just a little bit.
What you see is a cutout of the motor, and with this integrated solution or optimized system, we've got a hollow bore offering that we'll talk about a few of the benefits of the hollow bore. With our partnership, PBC essentially integrates that screw into the motor and allows for, again, a tighter package. We eliminate some of the mechanical components that couple the screw. It allows for a number of advantages and efficiencies on the customer side. Bigger bearings for your axial loads that are translated, etc. But we will touch on that a little bit more when we get into the details of the motor.
And if you can read the chart on the bottom left very well, then you have better eyes than I do. But perhaps Mike can elaborate a bit on what that means and what the back of the motor has on it there.
That picture is just a generic closed-loop control system. On the control side, we have the same basic drive interface that we had in the traditional system. But here, again, it's closely coupled to the motor and the screw for a tight integrated package. You get all the same local remote control options as in the traditional system, but here, again, they're optimized out of the box for the specific motor and lead screw combinations to really reduce the integration time.
Now we're going to talk a little bit about the nut. The nut that PBC is offering, which we actually just released as a general product release a couple of weeks back, is a patented anti-backlash design. If you look at the two pictures on the right-hand side, the one on the top is the PBC nut. We're calling this nut a constant force anti-backlash nut. And you can see it looks quite a bit different than the traditional anti-backlash spring nut. What we have found through great amounts of testing is that we are offering better than 2 times anti-backlash compensation using the constant force anti-backlash nut. This also offers a more consistent preload over the life of the system. To elaborate that a bit more, typically when you use a spring-loaded anti-backlash nut, as the nut wears in, the amount of preload varies, and it actually varies quite a bit. What that normally means is that when you have an application, you run it for some period of time until you see that backlash start to wear in, and then you have to go into your system and do some adjustments to compensate for that backlash change. The constant force technology essentially eliminates the need for that step as the backlash stays very consistent over the entire life of the nut. Also worth noting, the PBC line, which we are offering an anti-backlash nut, as you see here, and a standard nut, which is no anti-backlash. They're both going to be made as standard from a self-lubricated PTFE type of Delrin. And with that, we would recommend using no lubrication in the system, where with a traditional nut made of acetal or other types of plastic, traditionally lubrication is going to be recommended. We're saying this is 2 to 4 times better than traditional designs in terms of backlash and wear. The next slide is a 45-second video, which will go over a comparison of these two nuts side by side.
PBC is proud to introduce a full line of lead screw products featuring an anti-backlash technology we call Constant Force. The visual difference is evident. Let's take a closer look. The conventional design has a variable and inconsistent radial force, which changes dramatically over the life of the application. The traditional product uses a spring, while the Constant Force uses a band. The Constant Force band applies uniform pressure to the 3 fingers, which means the preload is consistent. Most importantly, testing has shown that our technology maintains preload better over the life of the application.
All right, on to the next slide. We're going to talk about the actual manufacturing of the screw process, which is done at PBC here in Illinois. We have come up with a unique roll threading process, and this unique roll threading process will help reduce the amount of pitting and flanks compared to a traditional lead screw. If you look on the pictures on the right-hand side, you'll see the PBC screw at the top is very smooth. where the screw at the bottom is much more rough and jagged. Essentially, what we found through lots of life testing is that the smoother screw helps reduce the wear on the plastic nut, which was able to allow us to get in excess of 6,000 linear miles in a system without failure. We also have a medical customer that had done some life testing and came up with very similar results. And of course, we'll put the asterisk in there and say, depending on the application, you may or may not see 6,000 miles. But we were very pleased with the results that we found in comparing traditional screw to the screw that PBC has come up with in our proprietary manufacturing process. Also note on here, and it kind of talked about it at the end of the video, we do have an online configurator already set up that will allow you to configure the screw, nut, or lead screw motor in its entirety and give you list pricing, CAD models, pretty much everything that you would expect in doing design type of work. To talk about accuracy a little bit, the screw that we are offering at PBC has about 2 to 3 times better lead accuracy than a standard industry screw. We're at plus or minus 0.003 per linear foot. Traditionally, it really depends on the actual manufacturer, but some of them go as high as 0.010 per linear foot. It's definitely better than a traditional screw. We've also got a sophisticated process for testing the screws to ensure that we're actually achieving the accuracy that we are stating. As you can see on the right-hand side, we're measuring every single screw that comes off of the line over the entire length. And we do offer, as a special, a precision screw that's 1,000, plus or minus 1,000 over the course of each foot. And lastly, I want to talk a little bit about the motor and screw integration, which was sort of alluded to at the beginning here. But essentially, the top picture shows you the motor, coupling, and screw. And the bottom picture shows you the PVC solution, which has the screw directly connected to the motor via laser welding. Benefits of this is that you've got factory alignment with the PVC solution, so it's coming to you guaranteed to be very well aligned. You're going to have fewer components, which is going to give you higher rigidity. And of course, with fewer components, you're going to have more reliability, and you're going to save money on couplings and other components.
If I could add one other thing, with regard to the integration of the previous slide, you're actually saving space as well. So end customer, the OEM, gets the benefit from either additional travel in the same package, or they would be able to reduce the size of their package, which obviously helps in tabletop solutions. Real estate is always a premium, regardless of where your machines are going. That is an added benefit to squeeze out that extra travel or extra space. Looking at the motors specifically, Moons is manufacturing over 10 million hybrid steppers a year and growing, and we're constantly innovating and looking at the technology to see where we can squeeze more out of every single motor we manufacture, whether it's our standard or looking at special technologies. I'll highlight a few of them. A couple of them are specific to the integrated package, but we're also looking at the entire motor technology and capability of Moons here just to highlight some of the benefits of working with a partner that specializes in motor technology. We do have products that are available with 30% more torque in the same package. We are able to do this by adding additional magnets into the rotor and actually into the stator and allowing the direction of the flux to increase the amount of torque output. This leads to better acceleration and deceleration performance, which inevitably leads to better cycle times, just improved efficiency on the customer side, as well as, again, the space savings in terms of the motor package itself for the amount of torque that you can get out of it. Interesting technology to apply to specific applications. For the hollow bore motors, we add larger bearings into the motors themselves because of the additional thrust coming from the screw and the linear translation. It allows for better support in the axial direction, which allows for longer life. We want to keep up with the 6,000 miles, I'll say, of linear translation from the PVC screws. We need to make sure that our motors can withstand that type of travel and life as well. And we do that by adding larger bearings in order to withstand that load. The hollow shaft concentricity, as Jamie mentioned, is factory established type of quality coming right out of the line. We make sure that the concentricity is tight on the hollow bore, which allows PVC to join the shaft onto the motor without having any sort of issues in terms of runout. This, again, inevitably leads to longer life, smoother operation, quieter operation. You're getting a quality product straight out of the factory. We add a preload to the bearings to eliminate axial play. So a standard rotary motor will typically have a wave washer installed on one of the sides of the motor, so either the front or the rear. What this does is it allows for a bit of play and give in a traditional rotary application, which is good because it extends the life of the bearing. But for a linear application where your positioning is critical, that's kind of the whole point here. You can't have essentially 0.9 millimeters of play sometimes with a traditional NEMA 17. It eliminates all of the accuracy, the precision that is required in a lot of these applications. We apply a preloaded nut to eliminate that play and allow for very good positioning in the linear applications. And then in terms of encoders, feedback, etc., quite often when you're relying on that precision and accuracy, you need the feedback to ensure you're moving, ensure you're in position. And it's standard for us to apply a rear shaft as well as have encoder holes on the back of the motors. That's easily done, and a variety of feedback options available from us, again, depending on the application requirements. Extremely flexible manufacturing, very customized for OEMs, very flexible, and top of the line in terms of technology and always pushing further. We work with customers quite a lot in understanding their applications and using our education along the way in order to provide them with the best solution.
Just a quick comment on that encoder mounting provisioning. The motor lines that we're offering for our lead screw motors are NEMA 8 through NEMA 23. And the Moons motors that Andy's talking about all have the two holes as standard in the back of the motor for that encoder mounting. And since it's a hollow shaft motor, you'd need to get an option to where the lead screw would actually stick out the back so that you can mount that encoder on there and get the encoder feedback if that's something that your application requires. The only one that doesn't have the holes would be the NEMA 8. I don't think they've got holes in that one, but the other ones all definitely do have encoder mounting capability.
If we move on to a little bit more detail on the special capabilities of Moons, a few of the things I'd like to highlight. There's a number of ways to address each one. Some of them I'll highlight here in regards to velocity, smoothness, and scanning. Jamie mentioned that all of the lead screws from PVC are tested for their precision and linear accuracy. And in terms of a scanning application, it's absolutely required to have that smoothness not only on the screw, but as well as the motion. We do have 0.9 degree step angles available. A traditional step motor is 1.8 degrees, so giving you 200 full steps per revolution. The 0.9 degree stepper cuts that in half and allows for 400 full steps. And again, with micro-stepping technology, which Mike might hit on, you're able to make those movements even smaller. We minimize the torque ripple through a variety of ways, but one of the main ones is to offer a three-phase stepper, which minimizes that torque ripple. We can talk about that more offline if anyone has any questions. High-speed motors, so we do have step motors that do actually get up to 8,000 RPM, if not 20,000 in certain special applications. This allows for us to get into a higher torque range. The slower you go, the more torque you have with a stepper, just to simplify things. By allowing the step angle to increase, we reduce the resolution. However, we push the amount of torque that you can get to higher speeds. Again, application dependent, what your requirements are for your linear speed and force, we're able to adjust either the type of motor we're providing to you guys or able to adjust the windings themselves, depending on what the application requires and the power you have available to input. Together with a high lead screw, either a 25 millimeter per rev or inch per rev, we have been able to achieve over 1 meter per second with a traditional stepper and a high lead screw. The speed range gets quite nice and the flexibility is there to address any application. Challenging environments, temperature extremes, we get up to Class F classification on the motors themselves. We've done higher temperature designs. It really comes down to the windings, the cables, the bearing life. We address those on an everyday basis. IP65, 67, beyond. We'll highlight an anti-corrosion technology that we also have available. We have seen a number of applications. We take that knowledge and it's available to our customers in order to benefit from that and get a shortcut in their design process. And then customized cabling and wire harnesses. Our company has a division over 600 people strong that focus strictly on wire harnesses, and that allows us to pass that benefit and optimization onto our end user, whether it's cables or connectors or shaft modifications. But in this case, PBC does a great job of that with the linear lead screws. You can get those customizations and configure those as needed. Mike, it's all yours.
Yeah, thanks, Andy. I'm going to talk a little bit about the step servo technology advantages that we mentioned earlier, and then a bit about your control options to make these systems actually move. On the right there, you see one of AMP's step servo integrated motors. So this has a Moons motor on the front and a full closed-loop control system with a 20,000 line incremental encoder on the back. So one of the biggest advantages of this step servo technology over a standard stepper motor system is that closed-loop servo-style performance. If you think about a classic stepper motor drive, it has a motor current setting, and the motor drive always delivers that set current into the motor regardless of the actual load. This means that you need to set your drive to deliver the maximum required at any point in your move, even when your motor doesn't need it. So as an example, if you need 5 amps to do a quick accel during a long move, the drive will deliver 5 amps during the accel, also 5 amps during the move, and also 5 amps during the decel to ensure that you won't stall and lose position. This means that during the long move in the decel, you're potentially burning energy you don't need, and you pay for that in motor heating and energy costs. By contrast, this step servo technology only delivers the current it needs to move the motor as requested. In that same example above, we'll set the motor current to 5 amps maximum. The motor will accelerate into the move and use the full 5 amps, but once that acceleration is complete, the torque requirements drop, and so the current backs off to the minimum required to maintain the desired move profile, using that 20,000 line encoder for reference. So this automatically lowers the current consumption of the motor, which saves energy and heat. Because that peak torque is generally required for a small portion of the move, usually the accel or the decel, we typically see heat loads reduced up to 65% as a result of that sort of automatic current adjustment. Now, in addition to dynamically lowering the current draw, the step servos have the ability to peak the motor current up to 50% higher than the rated current of the motor for short bursts, very short bursts. Again, taking that same example of the long move requiring the accel current burst, you can now potentially switch to a smaller motor, since a 3.5 amp motor can burst up over 5 amps for a few seconds to get you through that high torque requirement. Or, even better, if you keep the same 5 amp motor, you can actually increase your available acceleration current to 7.5 amps, which enables faster acceleration, and with a fixed move length, that means you can decrease your cycle time to increase your throughput with the same size motor. So now in this whole package, you have increased cycle time, and with the increased travel that the integrated screw brings to the picture, you really have a very efficient system. Switching gears to talk a little bit about motor control. You can see on that drive in the picture, which is our SSM series, there's a communications port, in this case it's Ethernet, and an I/O connector. The drives have 2 basic operating modes, standalone or streaming control, and we have a full suite of software configuration tools to help set up the drive as easily as possible. Standalone drives can be programmed using our Q programming language to perform complex motion profiles, react to analog and digital inputs and outputs, and manipulate registers. The programs can be executed automatically on power-up or triggered via digital inputs. And again, all this is configured through our software tools. Streaming commanded drives can be even more powerful when you have a PLC or other control system in the mix. In addition to being able to support stored Q program execution, the drives can be controlled and monitored in real time over your preferred communication protocol to monitor and command position, I/O states, and drive status. One key advantage here is mixed control mode operation. For example, on power-up, you can program the drive to execute a complex homing procedure and then set an output to tell your PLC that homing is complete and switch automatically into step and direction mode to await PLC control and give the PLC confidence that the drive is now in a known home position so it can start moving freely. And then finally, our drives support a lot of different field bus options for those PLCs. We have full commanded and stored program execution over Ethernet IP, EtherCAT, CANopen, Modbus TCP, and RTU, And we have a team of apps engineers in California that can support the various integration challenges from motor sizing and drive selection through field bus and PLC integration issues.
All right, let's run through a few different applications here. We're going to talk about what the applications require and how the integrated lead screw motor can be a great fit for those applications. First up is going to be a high accuracy positioning type of application. As you can see from the picture, we've got a DLP printer that's moving in a Z-axis direction. The key requirements for the application are a super tight 20 micron layer resolution. We've got retract followed by a step move. And of course, if you see the word printer in an application, it's almost always going to be very cost competitive. The way that the solution really shines here is for the screw and the nut, we offer the constant force anti-backlash nut, which is going to help with enhanced repeatability. The application is going to require bidirectional Z-axis moves. That's going to have a decent effect on the polymer viscosity, so it should actually be a benefit of using the type of nut that PBC offers. And then we talked about the improved lead accuracy of plus or minus 0.003 per foot, so that could potentially eliminate the need for an encoder, which of course, if you can start skipping out on encoders and then other components, you're going to save money on the application.
The smart motor here, this is going to use, as I was mentioning before, mixed control mode. The home to hard stop feature, which is mentioned at the bottom there, that allows you to have completely sensorless homing. You can write a program that's saved in the drive to monitor the position of the motor, turn the current down very low, and essentially move the screw until your load hits a hard stop. The motor can detect that very quickly thanks to that encoder, and you can back off and know, okay, now I'm in my home position. And then you switch over into step and direction mode, and the PLC can move knowing that you are in your home position.
For the next one, we've got a digital scanning application, which is going to offer a nice horizontal move. The key requirements for the application are going to be minimum torque ripple and a precise lead accuracy. Again, if we go back to the complete PBC lead screw motor solution, to summarize, we're offering a superior lead accuracy. For this application, it's definitely required. Any variation in the lead accuracy results in variable linear velocity, even if the motor RPM is 100% constant. Anti-backlash nut is going to also help in this application. The consistent preload and the ability to maintain a consistent preload over the life is also going to be very important.
In regards to the motor technology, the whole system here is important, not just one of the parts, but all of them. And with the addition of 0.9 degree stepper, the increased resolution on the full steps, this kind of allows for better motion across the entire plane, allows for better resolution. Paired with the controls of micro-stepping, just increases the ability to scan in a consistent way across the length of the travel. And then in terms of the detent torque, everything that I've seen in terms of other motors that are out there available, the detent torque is all over the place. I've found that Moons' motors have controlled that detent torque to a minimum and quite often are spec'd out much lower than competition. And this also improves the scanning capability without affecting the motion itself. I'll let Mike talk about the controls a little bit.
Again, this is using that same low torque ripple 400 pole motor that you mentioned. That really, with the 20,000 line encoder, we can achieve very, very precise move profiles. Not much more to say than that.
Okay. Let's go over to the next application. This is a high duty cycle application. It's another printer. This is actually going to look something like a company that some of you might be familiar with, a 3DP type of printer, where it's a large scale, large print type of application. On this application, we've got high precision X, Y, Z requirement. Of course, we're 3D printing, so we want to have layer resolutions around 60 to 70 microns. As you can imagine, when you're printing something, you need a lot of short stroke moves, but then you also need to be able to move long distances, up to 1.5 meters even, at a fairly quick speed. In this slide, it's saying 500 millimeters a second. You've definitely got to have a reliable life on your product, because a lot of these prints, especially if you're printing, as it says here, an engine block, or I know 3DP has actually printed large life-scale people. The larger the print, the longer it's going to take to print it. And the whole time the print is taking place, the lead screw, motor, everything else is moving continuously for that whole period of time. And of course, anything that has the word printer in it, it's got to be cost competitive because everybody wants to get it done for the least amount of money possible. Looking again at lead screw motor solution, we definitely want an anti-backlash nut to enhance that repeatability. We want to use bidirectional XY moves, which again the anti-backlash nut is going to help with. And then the lead screws that we offer have a variant lead availability. In this case, the lead that was being used is a 25 millimeter lead. We could accommodate all of those things with the PBC offering.
In regards to the motors, Jamie's mentioning the high lead and the higher torque available from the motor in order to improve efficiency and throughput on the customer side, because when they're printing things, they're not always necessarily printing, but they need to translate from one position to another, and the quicker you can do that, the more capacity you're able to get out of your print machine and process. Having a motor that's got more torque allows you to do that with higher acceleration, translate the move, and then decelerate a lot quicker, so you've got that fine control. In terms of missteps, etc., I'll let Mike talk a little bit about that because that's tied to the encoder and the controls.
One of the big advantages here, again, is that integrated encoder. When you think about a step and direction application, a lot of people think, okay, I'm going to feed a step in and the motor is going to move one step. With stepper motors without encoder feedback, that's not necessarily the case. The motor is going to try to move one step, but you have no idea whether or not it got there. With these types of smart controllers on the smart motor, you can feed in steps and the motor is guaranteed to move that number of steps. As long as your step input signal is clean, the motor is going to make it there, and it'll let you know if it's taking more torque, it'll let you know if it's taking longer than expected, but the motor will make it there.
Let's look at an application solution for harsh environments. And there's some gruesome pictures on the next slide that look at some of the different types of motors that can withstand that. For the screw material, we haven't talked about this yet at all. The video talked about it a little bit, but the screws are all 300 series stainless steel, so inherently those are going to be good for harsh environments. We do also offer a PTF coating option, which is why this screw in the picture is black. PTFE coating is going to reduce the wear. It's going to depend on the application again, but around 20 to 30% reduced wear. That's going to give you even more life. We do have specialty materials. Like I said, it's a Delrin self-lubricated with PTFE. We've also made custom brass and bronze nuts for customers depending on the application and their needs. And then, of course, the inevitable other options. If your customer has an application where they need something that doesn't look like we might have it, let us know. And if the opportunity is there for us, then we will definitely be glad to look into that for you.
This is an anti-corrosion technology that Moons has available. Typically what customers do when they've got a harsh environment is they try and seal all the electronics, seal the motors, and seal all the moving parts to avoid any sort of ingress of external material, whether it's liquid, dust, that kind of thing. With humidity and liquid in particular, chances are with the temperature changes of the motor, quite often the motor acts as a vacuum and inevitably some moisture will get sucked in. And if you're sealing the motor, you're trying to stop the material from getting into the motor itself, which will cause it to die eventually. But when you seal it, you're actually stopping anything that does come in from getting out as well. There's two ways to handle that type of application. And what we do with the anti-corrosion is we do not seal the motor itself, but we coat all of the surfaces. So we allow the moisture to come in and leave without affecting the performance of the motor. That's how we tackle that with this very unique product. All of the materials are coated, both internal and external, and the motor can run in extremely harsh environments. And you can see what type of salt water does to a standard motor on the left bottom picture versus to what the anti-corrosion motor looks like after the same amount of time in a saltwater spray test.
Okay. To summarize, what we talked about at the start was what a traditional lead screw motor looks like with the interface hardware and all of the other motion controls and et cetera that are required to make that happen. And then we compared that to the PBC solution, which is an integrated lead screw stepper motor. It's also really worth mentioning one more time that this can be ordered with one part number, which in its own right is going to help save you time, because you could go to one place, buy one thing that accomplishes everything that the application is going to need. So it's going to increase your performance with all the wonderful advances that Andy and Mike talked about, in motor and control technology. That's also going to reduce your cost, and it's going to reduce your size. With that being said, I'm done.
Thank you, Jamie, Andy, and Mike, for a very thorough presentation. That was very well done. If you do have questions, you will be able to reach the presenters. And I'd like to thank you guys again for an excellent presentation.